Hi guys, welcome back. Hopefully you had a relaxing makeup type week for spring break. We are starting our new unit, which is redox reactions or electrochemistry. Now, when it comes to this unit, it's a multi-step process, so meaning you're really not going to be able to understand how to do it completely until all and totally with everything until the very end. So we're going to learn like step by step how to do this. Um, when it does come to oxidation reactions, just make sure you focus on vocab and ask questions. You need to ask questions for this unit. We're gonna be practicing this for the today and tomorrow, and then Thursday, we're gonna move on to the next part, and then Friday there's gonna be practice for Thursday, as well as you guys wanted to have conferences, so we'll do that as well. If you do not want to participate in the conference, that's fine. But the conference is just basically gonna help you decide, okay, what assignments do you need to make up? What do you need to do over? Stuff like that. So we'll talk on that about that a little bit more later. So, like I said, redox reactions happen simultaneously. Redox reactions are another way we can say reduction and oxidation reactions. Now, when we have a reduction reaction, we are gaining electrons, and then when we have an oxidation reaction, we are losing electrons. That happens simultaneously, meaning you cannot have one without the other. You cannot have reduction without oxidation, and you cannot have oxidation without reduction. That is one thing you need to know. So make sure that you read the text that I gave you with the notes, because I'll give you a little bit more background about oxidation and reduction reactions, and then come Thursday, there'll be a little bit more background information. However, for us to be able to realize what is oxidizing and what's reducing, we need to be able to assign oxidation numbers. Now, we've dealt with oxidation numbers before, and that was when we were dealing with electrons, and we said electron transfer. And we said that when we had a positive charge or a positive oxidation state, that meant that we lost electrons. When we had a negative oxidation state or a negative charge, that means we gained electrons. That concept still applies. So positive, you lose, negative, you gain. That concept still applies. So, for us to be able to use all these oxidation states, some of you are probably wondering, well, how do I know which one to pick? For example, V has multiple oxidation states. How do I know what to pick? It's all going to be based on if V is attached to another element that only has one oxidation state, because then it only needs to cancel that one out. So what do I mean by that? Let's go. I had this as here as reference. We might flip back. Now some of my periodic table elements are cut off, so I might be using my phone to get you the other values. Make sure you have the periodic table so you can figure this out accurately. If you need to download it, you can get it on kentchemistry.com, or you can get it from the New York State site. It's there, it's a free download. Alright, so when we're assigning oxidation numbers, one thing you must be aware of is that the compound in total has a total oxidation state of 0, meaning it's a neutral compound. So it has a total oxidation state of 0. But the elements within the compound have their own individual oxidation state that cancel each other out. So if we look at Na and Cl over here, NaCl has a total oxidation state of, right, of 0. However, Na within NaCl has a total oxidation state of +1, while Cl has a total oxidation state of -1. However, NaCl in total has this oxidation state of 0. This is what makes it a neutral compound. If the oxidation states of each element cancels out to get a 0. Now, when it doesn't cancel out and it gives us a charge, that is also possible. But usually they'll indicate it. We'll talk about that a little bit later. But usually it will be indicated. So how do we figure this out? How do we go about this? Very easily. So first thing you need to do is you need to tell me how much of each element we have. Coefficients don't matter, but subscripts do. So magnesium over here has an subscript of 3, so it means I have 3 magnesiums. Nitrogen has a subscript of 2, meaning I have 2 nitrogens. Now I need to find out their oxidation numbers, because that's what I'm going to multiply with their subscript value to find out how much of that element what is the total oxidation state for that element, right? Not the total oxidation state for the compound, but for the element. So I'm going to go back and I'm going to look over here, and magnesium has an oxidation state of +2. So I'm going to go ahead and multiply that by 3. So +2 times 3 would give us +6. It's important to register the charges. Why is it important to write the charges? Because you need to know what to cancel out. If I have a +6, the only way I can cancel it out is with a -6. So that means nitrogen needs to be equal to -6 to cancel out +6. This is why the charges are very important to write. If you do not write the charge, it's just a number. So you must write the charge, right? So that means nitrogen needs to equal -6 to cancel out magnesium's +6. All right, but nitrogen has 2. So what is that individual oxidation number for nitrogen? Not the total oxidation number for nitrogen, the individual oxidation state for nitrogen. So I'm going to take -6 and divide it by 2 because I had 2 nitrogens, and that's going to give me -3. I then need to look on my periodic table to see, does nitrogen have a -3 oxidation state? If it does, I can use it. If it doesn't, I've made a mistake. So if I look on my periodic table, remember, I kind of cut it off over here, so I'm looking on my phone. And nitrogen has multiple oxidation states. It has -3, -2, -1, +1, +2, +3, +4, and +5. But I do see -3 there. So that means nitrogen's individual oxidation state is -3. And that still allows for +6 to cancel out with -6, which would give us 0. The goal of this is to get to 0. So let's try another one out. So over here we have hydrogen, which we have 1 of, nitrogen we have 1 of, and oxygen we have 1 of. All of the gens. And oh, not oxygen. Oxygen we have 3 of. Sorry. So I know that oxygen's oxidation state is -2. I'm using my periodic table to find this out. If you need to look at your periodic table, it is on the top right of that element tile. Alright? So it's -2. So 3 times -2 would give us -6. Right? So that means hydrogen and nitrogen together need to give us +6 to cancel out -6. So let's start with hydrogen, because nitrogen has a lot of oxidation states, while hydrogen only has 2 oxidation states. So if we look, hydrogen has a +1 and a -1. But we want to cancel out -6, so we don't want it to become more negative. So that means we're going to use +1 instead of -1. So 1 times +1 was obviously going to give us +1. Now look at this. We now have +1 plus 1 plus -6. That leaves -5 left. So to cancel out -5, we're going to need a +5. So that means n must equal +5 to cancel out the rest. So we need to look and see, does nitrogen have a +5 in its list of oxidation states? Once again, nitrogen's oxidation states are -3, -2, -1, +1, +2, +3, +4, and +5. Because it does have a +5, that means nitrogen's individual oxidation state is 5 plus 5, and its total oxidation state for nitrogen is +5. Now, the total oxidation state for the compound is 0, because +1 plus 5 plus -6 would give us 0. Alright. So the goal is to always try to make sure that the total compound's oxidation state is 0 while finding out the element's individual oxidation states. So over here, I kind of set it up already. So let's get started. So Ca, I have 1. O, I have oxygen, I have 2, because remember, there's 2 distributes inwards. And hydrogen, I have 2 as well. Remember, the 2 distributes inwards. So I'm going to start with oxygen, because oxygen only has 1 oxidation state, and that is a -2. So 2 times -2 will give us -4. Now, Since this gave me a -4, I got to figure out the rest. I'm going to go with Ca. Ca's oxidation state is a +2. So I'm going to go back here and I'm going to say, well, 1 times +2 is going to give me a +2. Well, +2 plus -4 leaves us with -2. So that means H needs to equal -2 to cancel out. Well, -2 divided by 2, H needs to equal a +2 to cancel out the -2 that's left behind. Well, +2 divided by 2 would give us +1. So that means hydrogen is going to be a +1. Let's do this last one over here. Magnesium, CO3. This can be found in your notes. Just go ahead and do that. Magnesium. So we have magnesium has 1. Carbon has 1. Oxygen has 3. So once again, oxygen has one oxidation state, which is a -2. So 3 times -2 gives us -6. Right? So magnesium, let's see, only has one oxidation state as well, and that is +2. So 1 times +2 would give us +2. So -6 plus +2 will leave us with -4. And since it's going to leave us with -4, that means C needs to be +4 to cancel out that -4. So, does carbon have a -4? I would show you on the slide, but once again, it cut off. So I'm going to tell you that carbon's oxidation states are -4, +2, and +4. So yes, carbon does have a +4. So carbon's individual oxidation state is +4. Carbon's total oxidation state is +4. But magnesium carbonate, MgCO3's total oxidation state is 0. Alright? Each element will have its own individual oxidation state within the compound. But the compound's total oxidation state will always equal 0. Alright. Gonna hear some thunder in a moment. Yeah, it's raining in New York. Alright, so when it comes to oxidation states, this is what's going to lead us into a little bit of Thursday. When it comes to oxidation states, remember, if the element is by itself, it's a 0. It has an oxidation state of 0. It can neither lose or transfer to anything. It can only lose or transfer if it's with another element, so it's in a compound. Alright? When we're dealing with only single replacement reactions are redox. Double replacement reactions cannot. We always need that element by itself. And obviously, the total oxidation states of all atoms in a compound is 0. So meaning the compound itself is 0, but the atoms or the elements in the compound have their own individual oxidation state. Now, to help you determine if it's an oxidation reaction, a redox reaction, it's very simple. And this is how we can go ahead and start off on Thursday's material. Well, the element is by itself, so its oxidation state is 0. So Mg has an oxidation state of 0. Cu has an oxidation state of 0. How do I know? They're by themselves, right? Now that I figured that out, I'm going to go ahead and look at Mg and O and Cu and O. Well, I have one of each element, so I don't really need to worry about, my setup. But I know that oxygen has an oxidation state of -2, so I always have that there, right? And then for this to be equal, the oxidation state, for this to be a true compound, the oxidation state in total needs to equal to 0. So -2, to cancel out -2, magnesium needs to be a +2. Right? And I could go and look at my periodic table to see, is magnesium a +2 oxidation state? Yes. And then to cancel out this -2 over here for CuO, right? Oxygen is -2. That means Cu needs to also be a +2 to cancel out, to make sure that the whole compound equals to 0. I just need to check with my periodic table.